Hello all, let's start section 2.7. 2.7 is rates of change in natural and social sciences. Uh, Actually, here you see the idea of derivatives, how we use derivatives in our real life or in other fields of science, like in physics, chemistry, biology, economy, or other fields of science, how we use derivatives. What is the meaning of that? Uh, I told you at the beginning of this class in one of my lectures that Sir Isaac Newton, when he was working on this book on calculus, when he found calculus, his main idea was to find the velocity of an object that's falling down in a specific time period. For example, after 5 seconds, after 4 seconds. And he knew on that time with the simple algebra, he cannot find that velocity. Why he creates calculus, that's the reason, and you will see it today. To start this lecture, let me graph something for you. Let me go a little bit back to the beginning of this course or to the beginning of this chapter, which when I graphed a curve for you like this, for example, I have a curve and I draw a secant line which intersects in curve in 2 points. Let's name this point x1 and here let's name it x2. Of course, if this point is x1, the coordinates of this point will be x1 and f of x1, which means y1, right? Instead of y1, I will write f of x1. Here, if the coordinates is x2, then the coordinates of this point will be x2 and f of x2. Now, if I draw my rectangle here, the distance from x1 to x2, you learned it in algebra, which we name it x2 minus what? x1, the difference of the distance, correct? And here, on this side, you have f of x2 minus f of x1, or y2 minus y1, correct? Which way you write. If I name, and even you know again from algebra that if I name x2 minus x1 delta x equals x2 minus x1, which is change, it means change in x, correct? And I can name delta y f of x2 minus f of x1 or y2 minus y1, correct? Let's name it delta x and let's name this one delta y. This curve that I draw, let's name our curve y equal f of x. It's a curve, any curve, correct? And the line will be the secant line. The difference of quotient, which you learned in algebra, the formula was delta y over delta x, correct? We call it the difference quotient. Actually, the difference quotient, delta y over delta x means f of x2 minus f of x1 over x2 minus x1, right? That's the meaning, x2 minus x1. This delta x over delta y over delta x, or f of x2 minus f of x1 over x2 minus x1, it shows the average rate of change. This one shows the average rate of change of y in respect to what? In respect to x. In which interval? Definitely an interval, in a closed interval of x1 and x2. Now, also, We named this one the slope of the secant line, correct? To find the slope of the tangent line, if you remember the beginning of this chapter, if I want to find f prime of x1, it means the slope of the tangent line. Let me put my page a little bit smaller. If I want to find the slope of the tangent line at x1, which is this point, the slope of the tangent line, this line, then f prime of x1 equals limit delta y over delta x as delta x approaches to where? To 0. Correct? That was the formula for the slope of the tangent line. Y2 minus y1 over x2 minus x1 as, or over h as h approaching to 0, but here we name it delta x, right? This formula actually means instantaneous rate of change of y in respect to x. This is the instantaneous rate of change of y in respect to x. That's it. Now, if the slope of the tangent line, which is the first derivative in a point, means the instantaneous rate of change, then we can use it in different fields of science, this idea to calculate, for example, in physics, velocity, acceleration, in chemistry, or in business, if I have the function, for example, for the cost, I can find the other parts of that using taking the first derivative. Let's talk a little bit about one example, which is example in physics. And after that, I will stop the lecture because more we will use the rate of change in section 2.8. And based on that, we calculate different problems, and you will see it in 2.8. But 2.7 is just giving you an idea how we are using the derivatives. Let's get an example of physics. In physics, at least one example from physics. Most of you have physics class and you will see this. S equal f of t is a position function. We call S a position function. What does it mean? For example, you have a particle which is moving on a straight line this way. S shows the position function, correct? And simple physics, maybe in a school, some professors, they name the distance d, some professors, they name the distance s. Here in calculus, we name the position function s. S is f of t, a function of time. When you are changing your position from point A to point B, for example, right? You need time. When you are moving from one position to another position, it takes some time. That's why we say the position function is a function of time. S equal f of t, correct? Now, if you take the derivative of the right side, correct? The derivative of the right side, which gives you ds over what? dt or ds dt in respect to time. If you take the derivative of a position function in respect to time, it gives you velocity, correct? It gives you the average velocity in that point. That's why Sir Isaac Newton, and you saw the example. Most of you are aware of the an apple is falling from a tree, right? Maybe most of you that you see that cartoon or something on Sir Isaac Newton. I don't know that's true or not, but his thinking was, okay, when this object goes down in 5 seconds, how much is the velocity? Then he found this calculus for us, correct? ds dt, which is the derivative of the position function, always gives you velocity, correct? Then I can write v equals ds dt. If I continue and take the second derivative of the position function, correct? The second derivative of position function is double prime, which is the first derivative of velocity function. It gives me acceleration. Then I can write acceleration equals dv over dt. Now, an example to explain this very well for you. I'll copy this example from your book. The position of a particle is given by the equation S equals f of t equals t cubed minus 6t squared plus 9t. A function of position is given to you, correct? Part A of this problem. Find the velocity at time t. It means find the velocity function. Very easy, easy. Velocity is the first derivative of position function. It means I'll take the derivative of this function. Then I can write v equals ds dt, which is equal d over dt of this function, t cubed minus 6t squared plus 9t. Then v equals, the derivative of t cubed gives you 3t squared. That minus the derivative of 6t squared gives you 12t. Plus the derivative of 90 gives you 9. Here you go. You found the velocity function at a time t. Correct? Part B of this example. In part B, they're asking you, what is the velocity after 2 seconds and after 4 seconds? It means when t is equal to, how much is the velocity? And when t is equal 4, after 4 seconds, how much will be the velocity? Easy to calculate. I have the velocity formula. V equals 3t squared minus 12t plus 9. I will find v of 2. Even you can name your v as a v of t. Correct? Now you're looking for the v of 2. Then v of 2 equals 3 times 2 squared minus 12 times 2 plus 9, which is equal, 2 squared is 4, 4 times 3 gives you 12, minus 2 times 12 gives you 24, plus 9. 9 plus 12, 21, minus 24, which gives you 21 minus 24, negative 3. Correct? After 4 seconds, v of 4 equals 3 times 4 squared minus 12 times 4 plus 9. Then v of 4 equals 4 squared is 16, 16 times 3, 48, minus 4 times 12, 48, plus 9. V of 4 equals 9. Correct? It means your velocity here is 9 meters per second, and here is negative 3 meters per second. What does it mean in velocity negative 3 meters per second? It means your object is going to the negative side. Correct? It's turning, it's going back. Later we will discuss this. Part C of this problem. When is the particle at rest? Okay, I have the velocity formula, V of t equals, or the velocity function, what was our function? 3t squared minus 12t plus 9. That was my formula or my function for velocity. When the particle is at rest, what does it mean? It means when your object is not moving. When it's not moving, it means your velocity is 0, correct? It means this function you should make it equal to 0. 3t squared minus 12t plus 9 equal what? 0. You make it equal to 0. This is the time that object is not moving, correct? It has no velocity. Now, can I first divide it's algebra, it's not even calculus. Can I divide everything by 3 to make it smaller? Then 3 squared minus 4t plus 3 equals 0. Can I factor this? Definitely yes. T and t, 3 and 1, both negative, correct? And if I solve this quadratic equation, t minus 1 equals 0, it means t equals 1. Also, t minus 3 equals 0. From here, t is equal 3. It means the object is at rest when in 1 second and at 3 seconds, the object stops. Actually, if I want to graph it for you, the object starts here. Here, your t is equal 0. Then it moves this way, correct? Here you have t equal 1. At t equal 1, it stops it at rest, like this. Then it turns back and moves this way, which come to t equal 3. Then it stops again and turns back and go. That's why you had there a negative 3 meters per second velocity, correct? Because you are going back this way. Here this way, correct? Let's do one more part of that. For example, let's find the acceleration. Find the acceleration at time t. The velocity function was Vt equals 3t squared minus 12t plus 9. To find the acceleration, I know acceleration equals dv over dt. It means take the derivative of this function. Then a equals dv over dt equals d over dt of 3t squared minus 12t plus 9, which is equal ddt of 3t squared gives you 6t minus ddt of 12t gives you 12, and ddt of 9 becomes 0. Here you go. This is your acceleration at time t. That's the acceleration function, correct? Now, when t is equal 4, how much is, for example, our acceleration? What you do, you replace t with 4. You are looking for a of 4. A of 4 equals 6 times 4 minus 12. Then a of 4 equals 24 minus 12, which gives you 12. That means your acceleration is 12. Of course, when you go in physics, we also explain to you the units. The unit for acceleration in metric system will be meter per second square, or maybe feet per second square. In our system, you will have a unit here. For example, for this problem, I'll just put for you meter per second square, but I'm not calculating because it's an calculus class. We don't care about here too much about units, correct? We just do care how we are using the derivatives in natural and social science. This was an example of the physics that I did for you in this lecture. There are examples of chemistry, examples of um, biology, examples of economics in your book. I let you to check those examples because some of you, you already had your chemistry class. Some of you, you are a major in economy or business major. You know much better than me those formulas, correct? As soon as you see, just remember what is the first derivative of that function, what is the second derivative of that function. It gives you definitely two more new functions, correct? And you can calculate and do different examples. I will stop my lecture in 2.7 here because in 2.8, I'll show you how you're using the rate of change in different examples, correct? Let's stop the lecture here and see you in lecture 2.8.